Hello, guys. Today we are going to talk about balanced forces. So that's when like one force balance out the other force. So specifically, this really goes into Newton's first law, which we know as an object in motion will stay in motion or an object at rest will stay at rest unless acted upon by an outside force. Some examples that we see this in is car crashes. So if you're not wearing a seatbelt, your body's going to keep going forward because an object in motion, your body in motion will stay in motion until it's acted upon by something else, the car, or the windshield, or another car. Now, typically, if we have an airbag or a seatbelt, it would be that which slows down our body. Another example would be boxing. The fist hits the face and your skull goes in motion, which causes it to hit your brain, which is what causes concussions. So just some real world examples here. Now, specifically, I want to go into that. What is a net force piece? So a net force is the sum of all of the forces acting on an object. Now, we're going to make sure we sum these in the X and Y direction separately. So I'm going to say the sum of all the forces in the X direction, the sum of all the forces in the Y direction. I want to show you that with an example that I've got here. So we've got an example of a box that has a 20 Newton force going to the right and a 5 Newton force going to the left. If I were to draw this as a force diagram, though, we would draw this as force gravity, force normal, and then we would have a 20 Newton force this way. We don't know what type of force it is. We just know the lengths, and a 5 Newton force this way. Now, if I were to sum my forces, and I'm going to say the sum of my forces, just like in math class, we use the same summation, the sigma, is in the X direction is going to be equal to 20 because it's going to the right. And then we're going to say minus 5 because it's going the opposite direction. Just like in vector notation from last unit, when they're going the opposite direction, we subtract them. So this would have a net force of 15 newtons. If I were to sum them in the Y direction, we don't know anything about it. But for now, we're going to say there's no acceleration because we're saying it's balanced. We're going to have equals 0, which would be Fn minus Fg. Now, you'll notice here, our net force is, if it's equal to 0, our object's at rest or at a constant speed. So that would be our Y direction here. However, if the net force is not equal to 0, that means my object is speeding up, slowing down, or changing direction, which is our X direction here. Now, we don't know which one of those it is because we don't know any information about the box. We don't know if the box is moving to the right or to the left, or if it's momentarily changing direction. We don't know that information. However, I do know that the box has a positive net force of 15. For this lesson, we are going to focus only on when they're balanced, so when it's equal to 0. So this is the focus of this lesson. The not equal 0 is our unbalanced forces lesson. So let's do a couple of examples with balanced forces. So we've got the situation given. The tension in the cable is 100 newtons. We want to determine the mass of the tire. Whenever I do problems like this, the very first thing I want to do is draw a force diagram. So I'm going to draw a force diagram of my tire. The tire has force gravity acting downward on it, and we've got force tension acting upwards. I'm going to draw my force diagram. After that, I want to start by summing my forces. So I'm going to say the sum of all the forces in the Y direction, because that's the direction we care about, is equal to 0 because it's just hanging there, which is equal to force tension minus force gravity. Force tension is positive because it's going up. Force gravity is negative because it's going down. Now, we know the tension here is 100 newtons, and we want to determine the mass of the tire. And you might be like, Ms. Schulte, there's no mass in here. But we know that force gravity, that's not supposed to be, is equal to mg. Now, I can move my mg to the other side, so I know that mg is equal to ft here. And I'm going to plug in my ft. 100 newtons. You can just plug in the 100, or you can leave your units in there. And we know G on Earth is 9.8 or 10. You can use either one of those. I'm using 9.8 just to be a little bit more precise, which gives me 100 divided by 9.8. And we have a mass of 10.2 kilograms for my tire. Okay. It's a pretty straightforward example. These are the ones I'm going to want you to be able to do quick like that. Let's get a little more advanced. Key and Jared are sitting on a board that's suspended by 2 cables. Key weighs 590 newtons and Jared weighs 850 newtons. The board weighs 180 newtons. The tension on one rope is 670 newtons. Use the idea that net force is equal to 0 to calculate the tension in the second rope. So we've got a lot of information here, but no picture. So I'm going to draw a picture to help us out. We are given the information that he has a downward force of 590 newtons. We're also given information that Jared has a downward force of 850 newtons. And we're told that the board, I'm running out of space on the image. Let's make a bigger dot. The board has a downward force, and this is not to scale, of 180 newtons. One thing I want to point out here, you see I'm not stacking the arrows one after the other. I'm just drawing them off the dot. That's what AP is going to expect you to do. We're also told that we have an upward force because the tension is going to go back up the rope of 670 newtons, and we need to figure out what the tension in my other rope is. So we're going to do a nice big long summation of forces. We're acting in the y direction. Sum of forces is equal to 0, which I'm going to do. I do all my positive forces first. So force tension plus 670. So those are my upwards add, minus 590, minus 180, minus 850. So all of those add up to equal 0. Pretty straightforward problem. We're going to say 0 is equal to FT. And then we're going to figure out what the number on the other side is going to be. So I do 670 minus 590 minus 180 minus 850. And this gives me a negative 950 newtons. So it means I have still an excess of 950 going down, which means that other rope has to have 950 newtons going up. I've got one more example for us. This example is going to take friction and bring it into play. So we don't have a lot of information provided, but we are told we just have a force diagram shown. We have a normal force going up of 12 newtons, a gravitational force going down of 12 newtons. We have an applied force going to the right of 10 newtons, and we have a friction force going to the left of an unknown newton. Now, keep in mind that this is a balance, so acceleration here is going to be equal to 0 because everything is balanced in this situation. So I'm going to sum my forces in the x and y directions just because that's a good habit to get into. And we know since there's no acceleration, we don't have to worry about that. So in the x direction, we have an F applied minus force friction. Now we know that the applied force is 10. I'm going to come back to that. In the y direction, I know we don't need it right now, but I just want to show you guys how we would do this. We'd have Fn minus Fg, which tells me my force normal is equal to force gravity, which we see that they're both 12. Most of the time, when you see problems like this, the acceleration being provided is the x direction acceleration. If there is a y direction acceleration, it will make sure that it's pretty clear. Now, force normal and force gravity are not always equal to each other. I want to make that very, very clear. I've got some examples for the additional videos that I'm going to make that will go into where normal force is not equal to gravity, but for simplicity's sake, right now it is. Now we get force friction is equal to 10 newtons. So that's what this one is. It's 10 newtons. However, we need to solve for our coefficient of friction. Now we know that force friction is equal to mu Fn. So if I know friction is 10, I don't know what my coefficient of friction is, mu, and I know force normal is 12, I'm just going to divide 10 by 12. And I get a coefficient of friction of 0.83. There's no unit with this because it's a ratio. All right. Big takeaways from this lesson. First thing you need to remember, like absolutely, summing your forces, if it's equal to 0, that means no net force. Summing your forces and it's not equal to 0, that means we have a net force. No net force means my object's at rest or it's moving at a constant velocity. Net force means my object is speeding up, slowing down, or changing directions, which is what that net force thing is Newton's second law, essentially. All right. If this makes sense, I really encourage you to watch the next couple videos. It's going to go into the trig piece of this. This is just the introductory level. So I would encourage you to watch whatever videos until you're like, I've got this, I can do this. I've got several different types of example videos because I'm going to go into a specific type of problem in each of those.